The Internet of Things, or IoT, is an increasing trend to take devices not normally thought of as computers and connect them to a network. A consequence of this connectivity is that the security of these devices becomes more important. If you do a Google search for phrases such as IoT hacks or IoT vulnerabilities, you can see there are plenty of people talking about this. One way that many of these attacks happen is that the attacker is able to pretend to be someone that they are not. Maybe I can convince your internet light bulbs that I am the cloud service that is supposed to control them. Or perhaps I can convince the cloud service that I am a legitimate user who should be able to control your lights. There are many aspects to security of IoT. Today I want to talk about identity and trust. Security isn't really a new problem for computers. In 1979, Kevin Mitnick accessed a DEC computer system and was able to copy software that was being developed. A lot of work has been put into making computers more secure. If you are watching this video now on YouTube, all of the data between YouTube servers and your computer is encrypted and protected through a system known as TLS, or the Transport Layer Security. TLS goes back as far as 1994, where it was called SSL. In the many years since 1994, computers have gotten more powerful. My desktop computer has many gigabytes of RAM, and the processor runs at several gigahertz. IoT devices, on the other hand, are usually much less powerful. It is common to have maybe only a few hundred kilobytes of memory, and a processor that is running at maybe 100 megahertz. However, since these devices are now being connected to the internet, security becomes that much more important. At the core of much of what is done for security is cryptography. Wikipedia defines cryptography as the practice and study of techniques for secure communication in the presence of third parties called adversaries. Before we move on, though, let's make sure we understand this word, communication. It is sometimes easy to think of communication as a live thing, maybe talking on the phone or texting someone. But communication can also be something that is stored. You are watching this video sometime after I made it, and while you are watching it, I will be doing something else. Cryptographers really like Alice and Bob. But as humans, it helps us to think about abstract things such as computers exchanging messages, instead as people with friendly names talking to each other. An easy way to think about security is to think about what things we would like to know are true. And one thing would be that we would like it to be true that someone outside of Alice and Bob, we'll call her Eve here, won't be able to know what the messages that Alice and Bob are sending to each other are. Determining what Eve can do based on what messages she is able to see is the topic of threat modeling, which would make another good video topic. A less obvious thing we might want to be true is that Alice and Bob are actually talking to each other. Our friend Mallory might try to pretend to be Bob when talking to Alice, and might pretend to be Alice when talking with Bob. Alice and Bob might not even realize that Mallory is doing that. It's probably a little hard to imagine if you think of them as communicating, say, over the phone, but maybe they are writing letters and Mallory works at the post office, or they are sending emails and Mallory has broken into the mail server computer. How does cryptography solve these problems? It develops something known as a cryptographic protocol. Wikipedia defines this as an abstract or concrete protocol that performs a security-related function and applies cryptographic methods, often as sequences of cryptographic primitives. A protocol is simply a formal way of communicating. It defines the exact messages that each party can send and what must be in them. The protocols themselves are built around what is known as cryptographic primitives. These building blocks are built out of things such as hash functions, and symmetric and asymmetric encryption. There are usually not a large number of these primitives, but they are really hard to come up with. Most of the primitives that are used now are developed over many years, often as a contest with cryptographers scrutinizing each other's work, the end goal is to make sure that these operations have the desired security properties, and that the implementations really do implement these operations. But the primitives themselves don't really give you security. That's why the protocol is so important. It tells you how to use them. If you look at the changes that have been made to something such as TLS, some of those changes are indeed due to weaknesses found in the primitives. But a lot of the changes come about because vulnerabilities were found in the protocols themselves. To wrap all of this up back to our topic, what is trust in regards to cryptography? Trust essentially means that a party will behave as it is expected to. Back to Alice and Bob, it means that Alice needs to be able to know that she's actually talking with Bob, and that what she says is what Bob will get. Trust is usually implemented using digital signatures, which will be the topic of the next video.